Hello everybody, this is Jim Corkins, and we are continuing on with 2.1 electric fields due to multiple charges. If you haven't done the reading, please do so. If you're in Physics 101 or 112, please read OpenStax Chapter 18 or Survey Chapter 15. If you're in Physics 131, please read OpenStax Chapter 5 and Knight Chapter 26. If you have the Coletta textbook, then please read Chapter 17. Okay? And again, this is related to your sapling homework number 3. Well, what we're going to be doing is we're going to be doing calculating electric fields due to multiple overlapping point charges. So up until now, we've only been doing one point charge in one dimension. So this is multiple point charges in one dimension, right? So that means we're going to have more than one vector that we're going to have to add those vectors and then calculate the electric field and quantify it somehow. Okay? So the basic procedure is this. What you're going to do to model those point charges and those overlapping electric field vectors at whatever point that you're choosing is you have to go ahead and you're going to draw a pictorial representation if one is not supplied. Okay, you have to establish a coordinate system. Typically to the right is positive, to the left is negative, up is positive, down is negative. That's the y direction coordinate. You're going to identify a point at which you want to calculate those overlapping vectors. Draw the electric field vectors at that point P. And then you're going to then go ahead and start creating equations to calculate that. Okay. So best thing to do is just try it out. Okay. So what we're going to do for instead of doing a tutorial example, we're going to do a problem much like the tutorial. Okay. And so in 2.1 we have an electric field tutorial. Electric field is 3, and you're only doing the top 2 panes. And essentially, you're going to be calculating the electric field at A, and you're given distances of D. And this first charge is a negative 27Q. The second charge is a positive 9Q. And so you would calculate the electric field at point A due to negative 27Q, which is a D away, and then and then add that to the electric field at A due to this positive 9Q, which is 1, 2, 3 Ds away. So we're going to be doing a similar thing, except we're going to be doing it in the horizontal direction, and we're going to be using this as, we're going to be doing it 5 ways, A, B, C, and D. Okay? So let me go ahead and mark up this document. I hit the comments button, put the arrow back in, and we're going to use black as our ink. And I think what I'm going to just do is I'm going to represent this. This is a distance D across for all of these. And this is a distance D across. Okay? Instead of using R. Okay, and what we're going to do is we're going to draw the electric field at the dot due to the 2 charges, and I'm going to change. Oh no, I'm going to leave this the same. Usually you want to have like multiples, right? But we'll just keep this as if you see a positive here, that's actually a positive Q. If you see a negative, that's a negative Q. And so what we're going to do is we're going to draw the electric field due to the positive Q at the red dot, which is a distance D away, and we're going to draw the electric field vector at the black dot due to the negative Q, which is 2 Ds away. All right, and so we don't have to model it; we just have to actually draw the field vector. So I'm going to call this guy this red charge. So I'm going to use red to outline the positive charges, and this is going to be red, and I'm going to make the second red This is a purple. Actually, make that maybe another color, like a orange. No, pink. I like that. Pink. This is a pink. So I'm coloring these so I could, when I write out my equations, you can see the difference, and also the vectors as well. And I'm going to use blue as negative for these guys, except for the bottom one. It actually has 2 negatives in it, so I'm going to use the left one as the left negative. And I'll use green as right negative. Alright, so I wanted to do that to just distinguish when I draw my vectors at that dot, which vector I'm drawing. Okay, so this positive Q is really close. It's only 1D away, and a positive Q has an electric field pointed away from that. So I'm going to draw this as this distance as the magnitude of this, 1D away. And this is the electric field is pointed in the positive x direction due to the positive Q. Okay. Now that blue charge in A is a distance 2D away. And I remember if it was distance 2D away from the last time, it was about 1/4 the size of a K, just a regular charge, a distance D away. So trying to remember the last, that was from 2.0, and it was the very last activity. So this electric field, the blue one, is going to be pointed towards the negative, and so that's pointed in the negative direction, and that's due to the negative Q charge. Don't mistake the negative Q has anything to do with the direction of the electric field vector. Okay, the negative Q is just telling us that the electric field is due to the negative Q. Okay. This positive right here is the direction of the arrow. So this red arrow is pointing in the positive x direction. That's why you got a positive in front of this. Okay. So hopefully that makes sense. All right. So now let's sum the overall electric field. Okay. Well, you have a right vector, and then you have a left vector. So my guess is the net electric field is going to be pointed about this far, because it's going to be positive. So this is the net electric field. That looks terrible. Rewrite it so it looks, so this is the net electric field direction. So I added red plus blue, and that gave me this. I walked 2 steps to the right and a 1/4 step back. I started here, I ended here, so that's why I got that. All right. So let's calculate the net electric field at A. And that's going to be equal to that positive Q's vector pointed to the right, and the negative Q's vector electric field pointed to the left. All right. And so now I'm going to define these. This positive EQ is going to be K positive Q all over distance D away, and that is a plus. And that blue one is going to be K times the negative Q. The negative Q goes in here, and it's a distance 2D squared in there. So multiplying this out, what you get is KQ over D squared pointed to the right. Then you have the K times negative Q outside the absolute value is just going to be KQ. And this is over 2D squared, which is going to be 4D squared. And so what that'll make is that will make this net electric field is going to be, if I factor out a kq over d squared, which I'll show you that right now actually. I'm going to factor out a kq over d squared, and you get 1 minus 1/4, and so that'll be 3/4 kq over d squared. Okay. So the size of this electric field vector right here is 3/4. Okay. All right. So that's the first one. Let's try another one. Why don't you try this one? Let's do B together. So I'm going to erase this and actually grab this part and bring it up top. In fact, I'll just put this here and call this 3/4 kq over d squared. And if you want to refer to this part, just reverse. What I'm going to do is have you do B. And then if you want to refer to the mathematics of how he did that, you'll just have to rewind this. But I'm about to erase this section. So why don't you go ahead and try B. And in the meantime, I'll erase this extra math, and then we'll do B together right here. Okay? So go ahead and pause the video and try B yourself. All right. Well, the steps are draw your vectors, your field vectors. So I'm going to draw the red vector due to the positive q on the left. So the positive q on the left is going to create an electric field vector pointed away from it, which will be to the right. And it's pointing in the positive x direction, E. And then I'm going to subscript it with what is causing that electric field. So there you go. You're going to have a rightward pointed electric field vector. And then you have another charge, a negative q, causing another electric field vector to the left. And that will be negative E. Well, that'll be in the positive direction too, and that's due to the negative q charge. Okay. Actually, let me see if I could move these vectors around. So let me draw this positive up here. I'm going to call it positive E to the positive Q. And then I'm going to draw another vector, which is going to be negative. It's going to be positive E to the negative subscript negative Q. All right. So I have two vectors pointing to the right, which makes me think that this is going to actually be 2kq over d squared. All right. So now we're going to sum the electric fields at B, and that is going to be equal to the positive E to the positive Q plus the negative Q's electric field, which is also pointed to the right. All right. And then if I'm going to plug in the values, that positive charge is a distance d away from the data point. So that's going to be positive kq over distance d squared. And that negative charge is also pointed to the right, and that's going to be k times a negative q all over a distance d squared away. And so that's going to be kq over d squared plus kq over d squared, which is going to in fact be 2kq over d squared. All right, that's looking pretty good. Let's see you do C. So why don't you try doing C, and you do it the steps that we did it. You draw the electric field vectors first, and then draw the and then go ahead and start creating your equations from the electric field vectors. Okay? Pause the video now. And we're back. Okay, so this positive, the data points here, the positive charge is going to be pointed to the right, and it's going to be small. And since that's 2D away, that's probably going to be about 1/4 the size of the blue vector pointed to the left. So electric field vector pointed to the right, positive Q is causing it. Now what we're going to do is going to draw the electric field vector to the left. That negative charge is only a distance 1D away. And now we're going to sum our electric field at C. I'm trying to be consistent with the procedure. All right, we have a positive E to the positive Q. And we have an electric field pointed to the left due to the negative Q. Again, don't mistake that this negative in front here has anything to do with that negative. Okay, it's just the negative in front here is the direction of the field vector. Okay, now that positive Q is gonna, the red charge, the positive red charge has got pointed, the field vector is pointing to the right, and that's K, and that's going to be a Q, and that is a distance 2D away that we're going to square. And then we have that negative charge, which is K negative Q, but that's okay, it's inside an absolute value, and it's a distance D away that we're going to be squaring. And so this is going to turn out to be a positive KQ. It's going to be positive 1/4 KQ over D squared, and this one is going to be negative KQ over D squared, which is actually going to end up being the opposite of A. It's going to be negative 3/4 KQ over D squared. All right. Why don't you try D? Why don't you pause the video and try D, please? And we're back. So you have the data point is here, and we're going to have a negative electric field vector pointed to the left. So it's an electric field vector pointed to the left due to the red positive Q. Okay. And then that other positive Q, which is a pink vector, is going to be pointed to the left, but it's 2D away. And so that's going to be negative, and that's due to a positive Q as well. So basically we have a full vector pointed to the left and then a quarter vector pointed to the left. Now let's sum our electric field at D, and what we will get is a negative electric, a negatively pointed, a left pointed electric field due to that positive red Q charge. And then we're going to have another vector pointed to the left due to the pink positive Q charge. Which is going to end up being a negative K positive Q all over. So this is a distance D apart. I can zoom in, I suppose. Make it a little bit easier. Oh boy, my handwriting's terrible at this level. Okay. And then that is the red charge's electric field. The pink charge's electric field is also a positive Q, but it's a distance 2D away. So we've got to square that 2D. So this is going to be a negative, that's going to be a negative 1 KQ over D squared. And this is going to be a negative 1/4 kq over d squared. So this is going to end up working out to be negative, what is negative 1 minus 1/4 was at negative 5/4 kq over d squared. All right. Yeah. Shoot. All right. All right. Let's do the last one. Last one's kind of a fun, easy one. A little bit on the silly side. Just notice this should be black ink right here. The resultant vector is just the addition of those two vectors. So all right. Well, the last one, E, go ahead and pause the video and try E, but just do the vectors, because you don't need to do the mathematics if what you're doing vector-wise can actually eliminate the math. But we'll do the math when I do it and just confirm it. But go ahead and pause the video and try the very last one. All right, we're back. Well, this data point here, we're going to have an electric field vector pointed to the left, and that's due to the negative Q charge. And then we have another negative charge. A little confused for a second. I thought I made that green. This is supposed to be a green charge. I want to use red for negatives because I want to try to be consistent. So this green negative Q charge is going to also have an electric field pointed towards it, which will be in the positive x direction, negative Q charge. Okay. So you take one step to the left, add that to one step to the right. So what you can see is that the net electric field should be 0, but we'll just confirm it. Net electric field due to E, which is going to end up being the negative E to the negative Q plus the green negative Q charge electric field is pointed to the right, and that's going to be equal to negative KQ negative Q over distance d squared plus a K negative Q over distance d squared, which is going to be equal to 0. All right. I've drawn out the answers more legibly here in the next page, so we can confirm what we're doing. Okay, and so as you can see, the net electric field on this part is going to be to the right. This one's going to have a doubly large net electric field to the right. This is going to have a 3/4 net electric field to the left. And this one is going to be the addition of those two vectors to the left, which will just be a larger electric field, this one plus this one size to the left. And this one will be a 0 electric field. So you can see, you can confirm those just vector-wise and estimate the size of those without having to do mathematics. Do the mathematics to actually just confirm your beliefs, right? So this is the basics of doing multiple, calculating a net electric field due to multiple charges in one dimension. Okay? I hope you enjoyed it. Bye.